Hey guys, welcome back. This is the Chapter 4 Supplementary review. I decided to do this because the brick and mortar class that I teach, the non-online version class that I teach, needed some more chapter review, and so then just naturally I felt like maybe you guys did as well. So decided to kind of gather some resources and put together another review, and wanted to make a video of me solving the review. So, as always, this document is available on Springboard. So the way that I would suggest that you guys go about handling the review is print it off, do as many problems as you can, and then come back and either look at the annotated version online or watch the video to watch me solve them to learn how to do it. So yeah, I don't know. I would say it's better for you to treat the review as like a worksheet and do on your own, and then come back when you don't know the answer to something, as opposed to treating it like lecture and just watching as I go along, because I think it tends to be really easy to not know what's going on when you just sort of kind of nod and say, yeah, I understand that, and just write along with me. So you kind of want to go until it's broken, and then go fix it, and then go until it's broken, and then go fix it, and so on and so forth. So rather than just following along. So yeah, if you haven't done that, I guess pause the video and pick back up in a little while when you have kind of hit a wall, and then come back to the video. All right, without any further ado, let's get started. Number 1. In an organization of 30 people, we wish to elect 3 officers: president, vice president, secretary. How many different groups of officers are possible? So we have a group of 30, and we're going to be choosing 3 officers. So this is just going to be our standard choose formula. So number 1 is going to be our standard combinations formula. So it's going to be, don't know why it's doing that. It's going to be 30, choose 3, which is, we know that the choose formula is big N, exclamation or factorial over little n factorial times big N minus little n all factorial, which is then just equal to 30 factorial divided by 3 factorial divided by 30 minus 27 factorial. Or, goodness. 30 minus 3 factorial, which is going to be 30 times 29 times 28 times 27, and then I'll cut 27 as 27 factorial. You'll see why in a second. And then 3 times 2 times 1 times 27 factorial. We can factor out the 27 factorials, and then we just get the 30 times 29 times 28 times 27, or times 28, all over 3 times 2 times 1, which is going to be 24,360 all over 6, which shakes out to be 4,060. All right, number 2, how many ways can we elect an executive committee of 3 from an organization of 30 members? So this is just saying how many ways can we elect the vice president, president, secretary. And basically this turns just this group of 3 into a multi-step problem. So we had 2 different counting rules. We had the combination rule and the multi-step rule. Combination rule we just saw in number 1. That's the 30 choose 3. And the multi-step was when you have different different steps or different buckets that you can put things into. So like if we have 3 different committee members, we have N1, N2, and N3, and we just are going to multiply the number of options that each different phase has, right? So if we were to look at this executive committee and we wanted to choose a president, how many different options for president would we have? Now, we're not talking about the whole 30 people. We're just talking about within the committee. Well, for president, we would have 3 choices, like assuming we've chosen a group. We would have 3 choices. And then given that we chose one for president, how many choices will we have for vice president? We would have 2. And then given that we chose one for vice president, we would have 1 left. So it's just going to be 3 factorial, or 6. Okay? And guys, yeah, don't hesitate to ask me questions in the discussion forum about this if you'd like as well. Number 3, how many different license plates can be created if a license plate must consist of 2 letters followed by a 4-digit number? Okay, so I'm just going to go ahead and say, we'll call that a symbol for a letter. I actually don't know what a symbol for a letter is, so we'll just say an @ symbol, dash, number. Okay. So that's kind of like it's not a formula, this is just like a visual representation of what the license plate is going to look like. Okay, but then now when we look at it like this, you can see that it's going to be multi-step, right? We're going to have something that goes into this slot, something that goes into this slot, something that goes into this slot, so on and so forth. Okay, and then we could view it as this is N1, N2, N3, N4, N5, N6. And then we would just multiply together the different options for each step. Okay, so the first letter, how many letters are there? There's 26 letters. Second letter would be 26 letters again. And then for the digits, we have digits 0 through 9, so that would be 10 digits. So 10 times 10 times 10 times 10. Multiply those all together, we get 6,760,000. On to number 4. Excuse me. If 15 people are available for jury duty, how many different juries of 12 can we obtain? Well, this is just going to be our combination formula. So 15, choose 12, which we know is 15 factorial over 12 factorial, 15 minus 12 factorial, which is 15 factorial, I guess, not factorial, we'll say 15 times 14 times 13. And we always want to take it down to whatever we're going to factor out. So times 13 times 12 factorial, all over 12 factorial, 3 factorial. So we cross off the 12 factorials and we get 15 times 14 times 13 all over 3 factorial, which is 6. And we get 455. We have 4 different flags and 4 slots on a flagpole. How many different arrangements of flags are possible? Well, this is clearly going to be multi-step because we have 4, and it literally uses the word slot, right? We have 4 different slots. So a slot would be N1, N2, N3, and N4. And if we have 4 different flags for slot 1, we would have 4 options. For slot 2, given that we've chosen one, we have 3 options, 2 options, 1 option. Multiply those together and we get 24 options. There are 24 combinations. We have 4 flags available for a flagpole with 4 slots, but the American flag assuming that it's in the group of 4, must be on top. How many different arrangements of 4 flags are possible? Okay, so this one gets a little bit tricky, but so we still have the 4 slots. Okay, and now we know that the American flag is in slot 1. So now how many options do we have for slot 2? Well, we still have 3 options for slot 2, 2 for slot 3, 1. So we have 6. A fancy meal offers one each of 4 appetizers, 5 entrees, and 2 desserts to choose from. How many different meal options are there? So this is again multi-step. We have an option here, an option here, an option here. So N1 would be appetizers, so 4. N2 would be entrees, so 5. N2 or N3 would be desserts, so 2. 4 times 5 times 2 is 40 options. If you roll a die 2 times, what is the probability of rolling a 1 first and a 2 second? So these are independent events. So we could view this as multi-step as well. So this would be the first roll, this would be the second roll. So the probability of rolling a 1 on a die is 1/6. Probability of rolling a 2 on a die is also 1/6. We just multiply them together to get the overall probability, 1/36, or if you put it in decimal form, it is 0.027 repeating. If you roll a die, what is the probability of rolling a 1 or a 2? So we're talking about actually rolling a die, just one roll. So the or is the key word here. So now we're getting into some of our elementary probability rules. So or, we automatically know that this is called the union. So the union formula. And the union formula had two different formulas, right? There was the one for non-mutually exclusive events and the one for mutually exclusive events. So we'll say non-mutually exclusive would be probability of A or B is equal to the probability of A plus the probability of B minus the probability of their intersection. Okay, and then for mutually exclusive events, it was just this without minusing off the intersection. Okay, so this event, is this non-mutually exclusive or is this mutually exclusive? Meaning, if it's non-mutually exclusive, the two outcomes can occur at the same time. Can we roll a 1 or a 2 can we roll a 1 and a 2 at the same time? No, we can't. Right? So you roll a die once. You can't roll a 1 and a 2. It's either going to be a 1 or a 2. So those events are mutually exclusive. So now when we're going to be calculating probability, I actually wrote that wrong, didn't I? That's a union. Now when we're calculating probability, we don't have like an intersection piece that we subtract off. So now we just add the probabilities of those individual sample space items there. So then we would say the probability of 1 union 2 is equal to the probability of 1 plus the probability of 2. And there's nothing to subtract off there. And so then we know that this is equal to 1/6. This is equal to 1/6. So together they equal 2/6 or 1/3 or 0.33333333. All right. So, on to the next one. I don't know why these are A's, B's, and C's. Oh well. What is the probability of drawing a king, a jack, and a queen in sequence? Okay, so this would be multi-step. So we have a first step. We have a second step. We have a third step. So we'll just say drawing the king, the jack, then the queen in sequence. So what is the probability of drawing a king, first off? Okay, so the probability of drawing a king, there's 4 kings in the deck, divided by the number of cards in the deck. So 4 of 52. Probability of drawing a jack, the second card, well now there's 4 jacks in the deck, but only 51 cards left in the deck. So 4 jacks, 51 cards. And then a queen, there's still 4 queens in the deck, but only 50 cards. So we multiply these probabilities together, and we get 64 over 132,600, and that equals 0.00487. What is the probability of obtaining 3 heads in a row if you toss a coin 3 times? So this could be considered multi-step as well. So there's 3 coin tosses, and the probability of heads is 1/2. The probability of rolling heads again has nothing to do has nothing to do with the first one because they're independent events. So 1/2 times 1/2. Whole thing is going to be 1/8, or 12.5%. If you draw a card from a deck of cards, what is the probability of drawing a king or a heart? Okay, so this is kind of what we talked about up here. These non-mutually exclusive union versus the mutually exclusive union. So first off, we notice that the question is asking us the probability of a king or a heart. So we know that it's union. We know that it's going to be a probability A or B. So it's going to be one of our union formulas. So the question is are these mutually exclusive events or are these non-mutually exclusive events? Because there is a king of hearts, because you can have a king and a heart at the same time, these are non-mutually exclusive events. So you could draw a heart and a king at the same time. So they're non-mutually exclusive events. So our formula is going to be the probability of A or B is equal to the probability of A plus the probability of B minus the probability that they occur at the same time, A and B. Okay, so then we'll say probability of K or H, and the probability of K plus the probability of H minus probability of K and H. So probability of king would be 4 of 52. Right, there's 4 kings in the deck out of 52 cards. Probability of a heart would be 13 of 52. There's 13 hearts in the deck. And the probability that it's a king and a heart is just 1 card, the king of hearts, 1 over 52. So 14 plus 13 minus 1 is going to be 16 over 52, which equals 0.3077. Sorry, I keep clearing my throat, guys. Okay, number 10. A skateboarder's top 3 tricks have individual probabilities of success of 70%, 80%, and 90%. What is the probability that he will go all gnarly and hit all 3 tricks in a row? Hilarious. My buddy Kevin wrote this problem, so he's just being funny. What is the problem that he'll go all gnarly and hit all 3 tricks in a row? So this is multi-step, right? These are 3 events in sequence. So N1, N2, N3. Probability of N1 is 70, probability of N2 is 80, probability of N3 is 90. We multiply them together, see if he'll go all gnarly, and we get 0.504. Following table shows information on class attendance performance for a group of business stats students. Find the probability that a randomly selected student had regular attendance. So this is just going to be marginal probability. So regular attendance, we would just go over here and we would find regular attendance. This is going to be 101. So probability of R is equal to 101 over 200, or 0.505. Find the probability that a randomly selected person had regular attendance and passed the course. So probability had regular attendance and passed. Regular and passed, we find that that's going to be 97. Find the probability that a randomly selected person failed the course given regular attendance. So probability failed given regular attendance. This is going to be, so we use our conditional form, probability of failed and regular divided by the probability of regular. So failed and regular, we go up the intersection of fail and regular and we see 4. So it's going to be 4 over 200. And then the probability of regular was 101 over 200. We factor out the 200s and we get 4 over 101, which equals 0.0396. Find the probability that a randomly selected person failed the course or had regular attendance. Or both is implied, even if it is not specifically stated. Yes. So we know that just from our union probability. So the probability that a randomly selected person failed the course or had irregular attendance. So probability of failed or had irregular attendance. So that's going to be the probability of failed plus the probability of irregular minus probability of failed and irregular. So we scroll up. Actually, I'll let you guys scroll up. Failed or irregular is going to be, so failed is going to be 32 over 200 plus irregular, which is 99 over 200, minus the intersection, which is 28 over 200, and we're going to get 103 over 200, which is 0.515. And then it says construct a probability table for this problem. I'm going to let you guys do the math here, but it is essentially taking all of these numbers in the contingency table and then just dividing out the total to get the probability. So I'll do the first one here, I guess, if I'm even able to with this pen. Let's see. 97 divided by 200 is equal to 0.485. Yeah, so on and so forth. So I'm just going to write in the correct answers and you guys can calculate them. Right, on to the next problem. The manager of a fast food restaurant found that 75% of customers order a dessert with their meal, 60% order a certain brand of cola, and 40% order both. What is the probability that the next customer who enters will order the cola but not dessert? So, but is like the negative version of and, right? So that's not going to be a given probability. That's going to be an intersection. That's the first thing I realized. But the first way that I want you guys to approach these problems always is write down what you know. Okay, so if we're writing down what we know, the manager of a fast food restaurant found that 75% of customers order a dessert. So we'll just say probability of dessert equals 0.75. And 60% order a certain brand of cola, so the probability of cola is 0.6. The probability of both, meaning they order both, so dessert and cola, equals 0.4. So then I make a contingency table. So we would say C, actually. Just fantastic writing. All right, so here's the beginnings of my contingency table. So let's write in what we know. The probability of D, the marginal, is 0.75. So then we know what not D is as well. We know what the total is. We know what C is, 0.6. So then we know what not C is, 0.4. We know the intersection between D and C. So we know that the intersection of D and C is 0.4. So then we know what the intersection of C and not D is, which is 0.2. Let's just go ahead and fill in the rest of the table just because we can. There. So now we're poised to answer any question that comes up. But now let's answer the actual question that comes up. What is the probability that the next customer who enters will order cola but not dessert? So it would be the probability of C and not D. So we just go find where C and not D cross. It looks like we have 0.20. So that's our answer. Okay. On to 13. One of the purposes of an audit is to detect the presence of errors in recording of accounting information. Suppose a CPA firm has been retained to conduct an audit of the accounting practices of a firm in which accounts are processed by two divisions, a wholesale division and a retail division. It is known that 60% of all accounts are retail accounts. Furthermore, it is known that 20% of all retail accounts and 10% of all wholesale accounts contain some type of error. Okay. So let's write down first what we know. Actually, first I'm going to make the contingency table with nothing in it. Or just one, I guess. So let's put in our information. So we have retail and wholesale, we can say, or I'll just say not retail. It doesn't really matter. And then we can say contain an error or do not contain an error. All right, and then let's write down the information that we have. So it is known that 60% of all accounts are retail accounts. So the probability of retail is equal to 60%. Furthermore, it is known that 20% of all retail accounts and 10% of all wholesale accounts contain some type of error. So they give us two probabilities there. So let's just split them and let's just think about them one at a time. Furthermore, it is known that 20% of all retail accounts contain some kind of accounting error. So given that it's a retail account, it contains an error. So the probability, given that it's a retail account, that it contains an error. And then likewise, probability, given that it's a wholesale account, it contains an error, is 10%. So before we do anything, before we even look at A, I just want to solve for the whole table, just because that's what I'm most comfortable doing, and I think that it's the most beneficial, because then you can just go back and answer any question that comes up. So I'll start to put stuff in the table. We got 0.6 for probability of retail account, 0.4 of not a retail, so of wholesale. And then we'll go back and we notice that we have conditional probabilities here. So as we always do this, we use our conditional probability formula to split these conditionals into the intersection divided by the marginal. Okay, and the reason that we do this is because these 4 slots in here are going to be intersection probabilities. That's all they ever are. So the parts on the sides are going to be marginals, and then the total in the corner there, and then the spots inside are going to be the intersections. So we have these conditional probabilities, and we use the conditional probability formula to equate it to an intersection over a marginal, and then that helps us to fill in the table. Okay, so we'll start with the probability of E given R, and that's just equal to the probability of E and R over the probability of R. And then we have the probability of E given not R, and that's equal to the probability of E and not R over probability, I keep writing R's, probability of not R. And now we then look at what we know. We have 0.2 for this one, 0.1 for this one. Probability of not R is 0.4, and the probability of R is 0.6. So we cross multiply, or so basically we multiply probability of R, like on this top one we multiply the probability of R to the left side, to both sides, and then we get 0.2 times 0.6, and then that's going to be the intersection of E and R. Okay, so 0.2 times 0.6 is 0.12. And then on the bottom here, it's going to be 0.4 times 0.1, which is the intersection of E and not R. So it's going to be 0.04. And then we can just fill in the rest of the table based upon that information. So we add up these probabilities and we get 0.16. We minus 0.16 from 1, we get 0.84. We minus 0.04 from 0.4, we get 0.36. And 0.48 right here. So yeah, that's that. So now we go to answer the question. If the auditor observes an accounting error in an account, find the probability that the account was processed by the firm's retail division. So if the auditor observes an accounting error in an account, so given that he observes an accounting error, so I'll just write it up here. Probability of something, given that he observes an error, find the probability that the account was processed by the firm's retail division. So there you go. probability of R given E. Okay, and we know that that's going to be the intersection of R and E over probability of E. Sorry, I ran out of room here, guys. But the intersection of R and E is 0.12, and the probability of E is 0.16. So that is going to be 0.75. Okay. And then we go to B, and B says, what is the probability that an account selected at random will have no accounting errors? So this is just the probability of not E. And we just look for the marginal probability of not E on our table, and it is 0.84. Okay. All right. So on to number 14. Stock market analysts have stated that the probabilities of the market rising, staying the same, and dropping are respectively 0.3, 0.5, 0.2. So I'm just going to go ahead and write those down right now. So probability of rise, probability of staying the same, probability of dropping. Okay, and this is 0.3, 0.5, 0.2. It is also believed that a tax surcharge will pass. So a tax will pass with a probability of 0.2 if the market rises, probability of 0.4 if the market stays the same, and with a probability of 0.6 if the market drops. Okay, so if is a word that is going to be synonymous with given a lot of the time, right? So like if we were to read this and just throw in given, okay, so it is also believed that a tax surcharge will pass with a probability of 0.2 given that the market rises. So then we can say the probability that's given here is given that it rises, T. So we'll call the tax surcharge passing and not passing, T and not T. Okay? So this is going to be 0.2. This is going to be the tax passing given stays the same. 0.4. And given that it drops, 0.6. We might need a little bit more room in this one, I think. So, as always with these problems, we want to write down the information that we have. Jeez, my computer's being funny. We want to write down the information that we have, which we've done, and now we want to put it into the contingency table. So we'll say 1, 2, 3, 1, 2, 3, 4. This contingency table is going to be a different size because we have 3 options in one regard. Right? Normally it's like a 2x2. This time we're working with like a 2x3 or 3x2 or something. So on this side we're going to have rises, stays the same, drops for the market. And we're going to have the tax pass and the tax doesn't pass. So for rises we have 0.3, that's the marginal, 0.5, 0.2. And now that's all that we can put in the table because we know that conditionals don't go in the table. But we can use the conditionals to come up with intersection points. So we use our conditional probability formula. So T given R, we know, is equal to the probability of T and R over the probability of R. And probability of T given S is equal to probability of T and S over the probability of S. And probability of T given D is probability of T and D over the probability of D. So we're just using that conditional formula just as we have been. And then for each of these, we're writing down what we know and what we don't know. So probability of t given r, we know that's 0.2 here. We know what the probability of r is 0.3, so we solve for the intersection point. So probability of t given or t and r is 0.2 times 0.3, which is going to be 0.06. And we do similar things for here. T given s, 0.4, probability of s, 0.5. So the intersection of t and s is going to be 0.2. And probability of d, we know it is 0.2. Probability of t given d is 0.6. So 0.6 times 0.2 is going to be 0.12. Okay, add those up to get the marginal of the tax passing, or t. That's 0.38. And we use our complementary rule, 1 minus 0.38, 0.62. We just fill in the rest of the table. All right, so let's just answer the question then. If the surcharge passed, what is the probability that the market rose? So let's see what this is saying. Given, remember if is given that the surcharge passed, what is the probability that the market rose? So probability is given that the surcharge passed, so given t, probability that it rose. And then we can also use our conditional formula for that, and that's just going to be the probability of rose and passed over the probability of tax passing, which is then RNT, which is 0.06, over probability of t, which is 0.38, and we get 0.158. Good, just 3 more. These are tiring. All right, 15. You might be interested in finding out a patient's probability of having liver disease if they are an alcoholic. I guess we're interested in that. Being an alcoholic is the test, kind of like a litmus test for liver disease. L could mean the event patient has liver disease. Okay, so this is just defining these. I got this off the internet, so you know it's good. So L could mean the event patient has liver disease. Past data tells you that 10% of patients enter your clinic have liver disease. Okay, so let's just write what we know then. So the probability of L is 0.10. A could mean the litmus test that the patient is an alcoholic. And it says 5% of clinics' patients are alcoholics. So it actually gives us this information as well. You might also know that among those patients diagnosed with liver disease, 7% are alcoholics. So given that they have liver disease, so given L, they're an alcoholic 7% of the time. Okay, so then we would just make our standard contingency table here. Uh-oh. Okay, so 1, 2, 3. So we have alcoholic, not alcoholic, liver disease, not liver disease. Let's write what we know. So probability of L is 10. So we know that total is 1, so we know that not liver disease is 90. Probability of alcoholic is 0.05, so we know that that's 0.95. And we know that we have a conditional here. So we use the conditional to come up with an intersection, right? And then we use what we have. So we have 0.10 for that. We have 0.07 for that. We multiply these together to get the intersection. So we get 0.007 for that intersection. So, sorry, that implies 0.07 is equal to probability of A and L. That doesn't equal 0.07. So 0.07 is A and L. So, or 0.007. So then we can use this to solve for the rest of the table. So we have the rest of the table, and let's just answer the question. So you might be interested in finding out a patient's probability of having liver disease if they're an alcoholic. So the probability of having liver disease given that they're an alcoholic. So given that they're an alcoholic, probability of having liver disease, and we just see that that's probability of A and L over the probability of L. So that's going to be 0.007 divided by the probability of L, which is it's divided by the probability of A, given that they're an alcoholic. Okay, 14%. On to the next one. All right. If a person gets a positive test result, what are the odds they actually have a genetic defect? So if given a positive test result, so let's call a positive test result T. So we'll have a T and not T eventually in our table. So here, I'll just go ahead and I can start the table now or later. It doesn't really matter. So we'll just say positive test result will be T. Negative test result would be not T. And let's just write down the question that they're asking us right off the bat here. So if a person gets a positive test result, so given that they have a positive test result, so the probability given positive test result, what are the odds they actually have a genetic defect? So then we'll just say G. So this is the question. So then we can have G and not G. So let's write down what we have. 1% of people have a genetic defect. So the probability of G is 0.01. So now we know what the probability of not G is as well. And 90% of tests for the genetic defect, 90% of tests for the gene detect the defect, true positives. So true positive means that we know that it is a positive test result given that the person does have the defect. So the true positive is given that they do have the genetic defect, it's true, and we know that that's 90%. And then 9.6% are tests are false positives. So it's positive test given that they don't have the defect. So positive test given that they don't have the defect, the genetic defect. If a person gets a positive test, what are their odds that they actually have the genetic defect? So we do what we always do here. We have written down what we know in our table, and now we have a couple of conditionals that we need to use. So we break the conditionals down into their intersections and marginals. So probability of T given G is equal to the probability of T and G over the probability of G, and then the probability of T given not G is equal to the probability of T and not G over the probability of not G. So we write down what we have. We have 0.9 here, we have 0.096 here, we have 0.01 here, and we have 0.99. Okay, and so we multiply through to get our answers. So 0.01 and 0.9 is 0.009. And T and not G is going to be 0.096 times 0.99. .095. Now we can fill in the rest of the table based upon that. Okay, and then we answer the question, what is P of G given T? That's going to be P of G and T all over P of T. G and T we know is 0.009, and P of T is 0.104, and that is going to be 0.087. So the probability a person gets a positive test result given that they do have the genetic defect is 0.087. So even though these tests seem fairly accurate, given that they get a positive test result, their likelihood of actually having the genetic defect is still only about 9%, or 8.7%. All right, last problem, guys. I'm going on an hour here. Yay. All right. Given the following statistics for women over 50, what is the probability that a woman has cancer if she has a positive mammogram result? So I'll do this the way that I did last time. I'll just make a contingency table right off the bat, and we can label what we have, what we know, and our labels. So we'll say having cancer and not having cancer, and then testing positive on the mammogram result as M for mammogram, which would be testing positive, and then testing and not testing positive. Okay, so that's what we know so far. And then it says 1% of women over 50 have breast cancer. So we write this down. Probability of C, 1%. We can put that into the table. Okay, and then furthermore, we know what not having breast cancer is as well. 90% of women over 50 have breast cancer 90% of women over 50 who have breast cancer test positive on mammograms. So who have breast cancer means given that they have breast cancer. So the probability of women given that they have breast cancer test positive, and that's 90%. And then and we know that these conditional probabilities are not in the table. And so then we have 8% of women over 50 will have false positive. So what's a false positive? False positive means that they test positively, but they don't actually have breast cancer. So given that they don't have breast cancer, they test positively. And that is 8%. So we normally do. We break our conditionals down into their intersection. And their marginal. to solve for what their intersection is so that we can fill out the rest of the table. So we know this as 98%, we know this as 8%, we know this as 0.99, we know this as 0.01. So 0.90 times 0.01 is going to be 0.009. So then we know this is 0.001. And then M and not C, 0.99 times 0.08. Actually need to calculate that because I didn't do this right when I was originally calculating this. Pause for teacher to calculate probability. 0.99 times 0.08. And that is 0.079. We'll just say 0.079. Fair enough. And yeah, I'd say rule of thumb, take it to 3 digits. And .911 and .912 and .088. All right, so we've solved for the whole table, so that's great. So now we just need to answer the question. The question asked is, given the following statistics for women over 50, what is the probability that a woman has cancer if she has a positive test result? All right, so given that she has a positive test result, so given positive test result, so M, probability that she has cancer. And we just plug in our formula. Jeez. C and M. And C and M we know is 0.09, and then probability of M, 0.088, and then 0.009 divided by 0.088 equals about 10%. So the probability given that there is a positive test result that a woman over 50 has cancer is around 10%. Okay. Seems like a low number, but that's kind of what you've seen in the last few problems here. That's kind of what Bayes' theorem is all about. There's a lot of medical examples, there's a lot of testing examples, and it works out this way because the probability of actually having these diseases or these conditions is so low that you tend to have a lot of false positives. And so that when you do actually take a test and you wind up positive, there's so many false positives that outweigh the actual true positives, so that given that you test positively, there's still a very small chance that you actually have the disease or the disorder or the cancer or whatever it is. So yeah, well, thanks for tuning in. I know this was a long video, guys, but did it for you. I want you guys to have as much information as possible. Yeah, so I hope this helps. Please don't hesitate to ask questions in the forums if I was unclear on anything in here, or if I missed something. I mean, there's a good chance I got something wrong, maybe. Yeah, thanks so much for tuning in, guys, and yeah, I'll release the Chapter 5 stuff shortly. Thanks so much.